This is a table I put together so it can give you some form of reference, and I use a reference of TNT, okay, as a kilogram of TNT, as I put it the number 1. So 1 gram of TNT is producing about 1 kilocalorie of if it is a TNT, so that would be about 4.2 megajoule per kilogram. Well, if you look at other things, a bullet, you can see, has only 1/100th, 0.01 of the energy intensity as a bullet. So bullet does not have much of the energy intensity, although it could have quite a bit of a power. Lead acid battery is not much better off. Lithium ion batteries, the one that's mostly used now in your cell phone, calculator, these are quite a bit of an improvement, but still is quite low compared to the what? Compared to the TNT. Compare that to sugar. Now 1 gram of sugar is about 4.5 times the energy than 1 gram of TNT will give you to your body. Okay, that's about 4.5 calorie, or big calorie in the food language, per gram. So 1 gram of sugar will give you about 4.5 kilocalorie or calorie, and 1 gram of butter, it gives you 9 calories. Gasoline has more energy than the butter, and the hydrogen has a lot more energy compared to TNT. The last line on this table, I'm comparing it to 1 gram of uranium-235. That's what we see later on is the fuel for nuclear energy, and that would be like 20 million times the energy of the equivalent mass of TNT. So you can see that looking at, let's say, gasoline, which is fossil fuel, 10, and uranium-235, which is 20 million, then you can say for the same mass, the nuclear energy has 2 million times the energy than the fossil fuel. That is the big advantage of the nuclear energy compared to the fossil fuel, and we'll talk about this quite a bit in the future modules. So we understand the difference between the energy and the power. In short, we define the power as the work that you have to carry per unit time, how fast you're carrying the work, and of course, because the work is force times displacement, and displacement divided by time is velocity, it can be equally represented by the force times velocity. The faster you move the force, the more power you need. The shorter the time it takes to do certain work, the more power you need. These are two basically different forms which are representing the same thing. So the question comes about is that, do we need more energy or we need power? Well, that it depends. Let me give you an example. You want to move from Los Angeles to San Francisco. San Francisco is about 300 miles away from Los Angeles, for those of you who don't live in the area. Usually a gas full of tank will take you from here to there. What you need to do, you need to use the energy. You need the gasoline in the car. And as long as you have 1 tank of gasoline, you can get from Los Angeles to San Francisco. So energy is what we need to go from here to there. And that doesn't really matter too much whether it's a fast car or it's a Porsche or it's a Toyota or it's a different kind of model. Well, assuming they have the same efficiency, then a different cars that they have same amount of energy should get you from one position to another position. However, if you want to get to San Francisco in a shorter period of time, or you want to go faster, in this case you need more power. That means you have to burn this energy over a shorter amount of time. A Toyota can burn, this energy, let's say in 6 hours or 8 hours. A slower car. A Porsche can burn this thing in 4 hours. So you get from here to there in 4 hours. What's the difference between these two? The difference between these two is not the energy that they use. They both use roughly the same amount of energy, namely tank full of gasoline, but the Porsche use this energy over a shorter period of time, so you get faster there, so it uses more power. To use more power, of course, you need a bigger engine. So bigger engine is more powerful, which means it can run the energy, use the energy in a shorter period of time. This is the power output for a few basic machines, that you can compare them. A laptop, it uses only about 10 watt. That means every second that it runs, it is using 10 joules of energy. Watt is a unit of power, which means joule per second. We use certain amount of energy just to be alive. There are several bodily functions that they need energy. Okay, so we need, even the energy to breathe. Even whether we were asleep or we're awake, in a very, very sedentary position, that means not much, physical activity, we still need the energy to maintain our body temperature and our normal functions of our organ. On the average, a healthy man, is using about 100 watts, no matter, if it is at rest. Of course, if this person will do some activity, then he's using the energy much faster, so you need more energy. You burn up more energy in a shorter period of time, so we use more power. A horse, in a continuous basis, it can produce about 750, to be exact, is 746 watts of energy. This is what we mean by 1 horsepower. So a horse, it can continuously produce that much power on the regular basis. Well, can a human being produce that much power or not? The answer is yes, maybe, but only for a very short time. A man which is running, on maybe a treadmill, can use 400 or 500 watts of energy, but then it gets tired after 20 minutes. So it can produce 500 watts of energy in about 20 minutes. It cannot run that energy continuously. A horse can. A top level athlete, and he can use maybe 2 or 3 horsepower, but only for 5-10 seconds. That's when the 100-meter dash, the Olympic runners, they produce a lot of energy, but only for a very short time. A lot of power, I'm sorry. Your average automobile can use few hundred kilowatt. I put 100 kilowatt, as order of magnitude. A gas turbine is 10 times more. Large power plants, like a nuclear power plant, they produce 1 gigawatt of power. So one power plant can produce over 1,000 times more power than a gas turbine, which is 1 megawatt. And a gas turbine or water turbine, they can use about 1 million times, or maybe 1,000 times, of the regular man. 1 million times a regular man.